about important ones, I would say understand this term thoroughly. Covariance stationary. See, there are we will talk about that in detail. So covariance stationary and white noise, important one. AR1 moving average, and again ARMA like autoregressive moving average, and then autoregressive moving average. And testing autocorrelation, this is a part that I was referring to, that you may have to apply a bit of your understanding from hypothesis testing. So yeah, high level, 1, 2, 3, 4. Like, of course, if you understand ARMA separately, you will understand ARMA and autocorrelation. So this is a very high level introduction about this chapter. So let's understand what's covariance stationary, a time series. See, firstly, let me emphasize that we in this chapter we would be talking about stationary time series and not non-stationary time series. So yeah, so non-stationary is a separate chapter, which we would be doing next time. This time it's just a stationary time series that we would be covering. So if I talk about covariance stationary, see, stationary time series is a very big term. Like in general, if I say stationary time series, it has to follow like bigger set of rules. Whereas if I just talk about covariance stationary time series, it has to follow, first of all, like let me explain you what is a time series. See, it time series is anything that you plot against time. So for example, this vertical axis here is your return axis, and on horizontal axis you plot time. So how your returns are moving over time. So if we plot, say, from 2015 till 24, or say 2014 till 24, how your return of certain stock, index, or portfolio have moved, that is time series. And when I say covariance stationary, it has to follow certain rules. First rule is its mean, that is average, should be stable over time. Okay, very important one. Like if you notice, like in this case, in fact, this is a mean, but there could be some time series. Say this is a time, this is a return. Some time series could be there, which might be like shifted upwards on the x-axis, like it's slightly above than this, but it will also have some average mean. So the mean of this time series should be constant. Mean should be constant, and variance might be finite and stable over time. Very important, please remember this. I will explain you like intuitively also, but yeah, two things: mean should be constant, variance should be finite and stable. Then covariance structure must be stable over time. Like your, when I say covariance, your variance with the previous term. But yeah, let's focus on first 2 points primarily. Your mean should be constant and your variance should be finite and stable. So like, are we clear that it's your mean shouldn't vary? Of course, over a period of time, if some stock is giving uh returns over, like, say for example, this decade, 2014 to 2024, average return of this stock should be, say, it's 10%. Average is 10%. But say if I talk about 2004 till 2040 14, if the average of this stock itself is, say, 8%, but it is also constant. See, there would be variation against a longer time horizon, but on a considerable time, the mean should be constant. Then you say the mean is constant, stable over time, and the variance is also finite and stable over time. When I say variance, this is a distance that I'm talking about. How far these like the variations are there. These should be stable. There shouldn't be something like this shock. This is something which you can say it is a shock. But yeah, if your variance is stable over time and finite, then you say your time series is covariance stationary. Any doubts till these 2 points? Understanding time series, understanding what is covariance stationary, or what are the two criterias that should be fulfilled for time series to be called as a covariance stationary. Any doubts? Anyone? Like, all good?
Yeah, I'm good.
Yeah.
Good.
Yeah. So this is something, and now I'm coming to intuition. This is something which you need from the syllabus perspective. I covered that. Now, if I were to talk about intuition, okay. So intuition is like, see, this is a like wave. Okay. Say for example, if you have got something, this could be returns. See, returns are sometimes you have positive returns, sometimes your returns go low, and but if you see, if I plot stock, this could be of the returns. But if I talk about stock prices, this could be like of course there would be like zigzags in between, but largely it would the stock price over a period of time it would be increasing. So for this one, be very careful. This is a contradictory example I'm giving, which we this is a second class of time series that is called as a non-stationary, that we would cover in the next chapter. Something which is kind of your mean reverting, or mean is stable over time, that those class of time series we would study in this chapter. But something, say stock prices, that is something we would cover in the next chapter. But yeah, just get an intuition, something which returns to or the mean is stable, then you say this is a covariance stationary. Stationary isn't something which is like kind of static over a long period of time. Stock prices, these are like you can say, if you plot 2014 to 2024 for a same stock, you will certainly get something which is non-stationary, because there would be upward trend, unless there is something like COVID that would bring down the prices for certain time window in that decade. But largely it would be upward trending. Do you guys agree? Any other thoughts in general or comments?
Yeah, I'm good. I'm good.
Dr.
Yeah.
Star? Good. Thank you. So this is something which is actually from the live data. Like if you are interested, you can explore. For Apple stock, if you pull out the data, like you get a sense, right? Like the mean is somewhere, like this is something which is like mean, you can say, and your daily returns, which like are wobbling between, say, like let's keep 10% and minus 10%, I would say. So yeah, this is something which you can explore. And if like just to get an intuition of covariance stationary for stock returns, largely your time series are covariance stationary. And if you're interested, like institute offers something in finance, like if you're a finance professional, if you want to learn tools to have these kind of plots, or understanding things better. Because see, if I just as a see, as a student also, if I'm just reading these 2 points, keeping in mind and going to exam, I may crack the exam. But something, if you go extra mile and understand things bit in deeper, that will like shape your overall like the career trajectory. So like any of your peers also are interested, please do like share with them, like, and they can attend. Like of course this is something which is very advanced, I would be open. This is something which is very advanced, but yeah, just to understand basics of this, what are functions, what is list, like the dictionary, like these kind of stuff, like you can explore. And then for like you have subject knowledge club with the tool that can help you a lot. So yeah, just share with anyone who might be interested in. Coming back, the time series definition we already talked about. And like let's time series definition we already talked about. I think a header should have been auto covariance and auto covariance and autocorrelation function. So the correlation between the current value of time series and its previous t periods in past is preferred as autocovariance. Can you tell me, we talked about covariance formula in our initial classes. Can you tell me, first of all, let's talk about variance. What is variance? Like we I think we got stuck in one of the numerical that we were solving yesterday, TSS deviation, like SSR, wherein we picked up the formula for variance. Can you tell me what's the formula for variance? I can relate it then with covariance. Yeah.
Then minus mean.
Yeah. Data point minus your mean.
Hmm.
In general, is this is something square deviation square over n.
Divided by
And
n.
just to be clear, yeah, this is something which is TSS from our regression thing. So now if I talk about covariance, see, this is a variance we talk about when we have one variable. When we have got two variables, it is product of these deviations instead of square. Over there, say for example, I've got two variable x and y. What I'll do, I will uh, I will just take a data point, take a difference from mean, then take another variable. Like when you have got two variables, you have got array x, y. You can do, like, you can calculate x bar for this, y bar for this. Distance of each data point from mean, this will cover here, y minus y bar over, and divide by uh your, again, it's same, n over n or n minus 1, depending on what you're talking about. It's a population or sample. So this is something that you like, it's a covariance. But now over here, when it comes to time series, we talk about autocovariance. So when we talk about autocovariance, like instead of two variables here, x and y, I can talk about like variable, one variable. Like say for example, this is value of t versus value of t minus, value of itself at t minus 1, and again like value of t minus 1, value of t minus 2. Like you can again have a two arrays. You can give it a something, like if you're comfortable you can give it name to y. But technically when we talk about auto means itself, it will have the values of variable itself, but it will have a one lag value like covariance, and then you do a same calculation, like no other change. Then that is called as a autocovariance, and it's autocovariance for all t. Like say for example, if I'm just saying, you talk about lag. So if I talk about t versus t minus 1, or say in general, let's talk about t versus, like this time series is for t, and this time series is for t minus k. So when your k is equal to 1, this is the case that I was talking about. You collect t, over here it would be t minus 1 and t minus 1, t minus 2. Like this, something which you collect, you calculate covariance. It lag can be 2 also. Like you can have a like comparison of first variable versus your uh like the second lag variable. That could be anything. Okay, it's autocovariance for all. Tau make it autocovariance function. Of course, like when you do it for different lags, you get a autocovariance function. If a time series is covariance stationary, its autocovariance function is stable over time. Like it's goes like quite intuitive. Like if your if your time series is covariance stationary, your autocovariance function is also stable over time, because somewhere, because you will have a constant mean, and if your mean is constant, somewhere this quantity also would be stable over time. So and to convert an autocovariance, and can you tell me what was the formula for correlation when we were talking about two variables in general?
Covariance of x and y divided by sigma x into sigma y.
Okay, same thing we do here. To convert autocovariance function to autocorrelation, we divide autocovariance, like how we were doing covariance. Over here it would be just autocovariance at each t by variance of time series. You just divide a like over here, like it was a standard deviation of xy. But if my x and y are like largely same, so it would be variance of time series. Instead of two variable, it would be a sigma x only. So sigma x times sigma x, it would be sigma square x. So that's why it is saying variance. This is a variance that you would divide autocovariance of xy over variance of time series. Is it making sense? Yes, no? Like if not, I have something to share with you. I'll just go like, is this entire thing to get a better understanding. I have something, but see, to be honest, that is not that important. This calculation is not important. Why I'm sharing this? So that at least you know what these terms are. Otherwise, like sometimes you would have, that what is a autocorrelation. Autocorrelation is correlation of variable with its lagged variable, right? So meaning, but sometimes if you know the calculations also, things are much clearer to you. So that is the reason. But any doubts in this slide? Otherwise, I can show it to you, like how you can calculate this, and we can go ahead. Any doubts so far?
Yeah, I'm good.
Okay, let me share then the calculation. Again, I'm reiterating that this may not be that important from exam point of view, but just to get an intuition that what exactly this means. Like you can think of, like, say for example, in time series you have these five values, say returns, like just for sake of understanding. First you calculate your average, as I said. Then what you do, say for example, you take a lag one. See, we were talking about lag tau. It could be anything like lag one. What you will do, you will just take this is one, and then you put one. This in general can be k, like you can put till k. And what you are doing is essentially the average would be same for all values. Then you just put t and t plus 1. So like t would be, like over here, if you see, the x1 is your 10, x2 is 12, x14, like all the 5 for our series, we have this all 5 values. And when you calculate covariance, when you apply this formula, in numerator it would be 4, because n minus 1, we are talking about sample, it depends what you're talking about. And then you take your data point difference, and again your xt plus 1, which was 14, which was 12 here, and you take t plus 1, like the variance of t plus 1 versus t, and the deviations from mean you multiply. Likewise, what you will do, you will do it for 12 and 14. So 12, 14, you can just multiply the deviations. Likewise, you can do it for 14 and 16 here. 14, sorry, this one 14 and 16, this is the average. This 14 here is the average that is coming from here. So 14, 16 and 16, 18. 16, 18 and like the mean is 14 again. So there would be 4 pairs, like 1, 2, 2, 3, 3, 4. Ideally, we can talk about 4, 1 also, but yeah, let's stick to what the current practice has been. One can argue that ideally there should be another pair also, which will talk about this one. But it is, I think, it would be too old if I compare this data versus this data. Perhaps it would be too older. That's why we are not talking about it. We are just talking about something which are closer. Intuitively, that is a reason one can give, like why we are not taking 5 and 1, because this is kind of your 5th month return, and this is kind of your 1st month, and we are just talking about something which is quite closer. And then you have a covariance, and
Please, I lost you when you were cycling the is it 10, 12, then 12 again, and 14 and 14 again.
let me this one, let me just which one do you didn't follow? I can explain you.
Yeah,
See, let me just make it very simple for you.
yeah, this side. Yes.
Let me just make it simple for you. And so they say, for example, this 14 here, these are average that we calculate, because we have to calculate the distance from the mean also. So these are all averages. Then what you do, yeah, this is something which is 1st month, 2nd month data. So 10, 12 deviation of this. Then 12, 14. So this 12, this 14, 2nd and 3rd data point, this one here, and this one, this 2nd and 3rd. Then you take 3rd and 4th data point, 14 and 16. So 14 and 16 data point, this is the average data points distance from the average. 14, 14, 16, 14. And finally, we have 16 and 18. So 16 and 18. You just multiply deviations, add these up, divide by 4, get your covariance. This is called as a autocovariance. Are we clear, D'Costa?
Yeah, so the difference between the autocovariance calculation and the covariance calculation exactly is it the repeated value? Because that's where I'm getting lost.
Sorry, maybe I did not get your question. Can you repeat, like, what exactly, or you can refer some values and tell me your question?
So you see, with the normal covariance calculation, it would
Mm.
have been 10 minus 14,
Mm-hmm.
12 minus 14,
Mm-hmm.
14 minus 14, 16 minus 14, and 18 minus 14,
Mm-hmm.
right?
No, that is for normal variance. See, only difference being, like, over here, your two strings, like ideally, if I were talking about two variables, over there, my first value would have been 10 and second value. So this is my xi, this is my yi. Ideally, like, because it is a variance with itself, we are taking the lag value, or like one value ahead and this value. But had this been two variables, we would have talked about two different values. Say this would have been my series 12 14 and 14 16 and 16 18. And say if my x bar is 14, and for sake of understanding, assume that y bar is also 14, then again you can replicate the normal covariance formula. You can translate normal covariance formula into this equation. The only difference being, instead of two variables, we have one variable. I'm not sure if that addressed you.
Okay.
Still, any doubts? Like, I can, I mean, if you can exactly spot center of your query, then this is something I shared in. Yeah.
I get it now.
Okay, cool. So next one is, say for example, if you talk about lag 2. So this was lag 1 when you were taking.
Sorry, just a quick one. So lag 1 is the normal covariance, right?
Yes, lag 1, instead of two variables, the second string of array that we have y variable, it is from the same variable, but it is just a lag value. That's how you can think of autocorrelation with lag 1.
Okay.
Make sense?
Yes.
Okay. And when you talk about lag 2, see, these are of course not in your syllabus. You're not expected to know these results, but this is something which I'm just sharing so that you will remember at least. Otherwise, if I just tell you autocovariance, and if I have 1 month down the line, if I ask you what is autocovariance, you may be little lost. With this type of additional explanation, you will at least remember, yeah, we had talked about lag 1, lag 2, lag 1 is not normal autocovariance. So you will remember in that way. And leg 2, like in leg 2, what will happen, like this formula, ideally over here it is n minus k, and this also would be n minus k, which is leg 2. We had n as 5, and if I'm talking about tau as 2, so this would be till third. Now what you will do, you will just consider xt and xt plus 2. This bar will remain same, so 14 will not change. Let's see how my xt and xt plus 2 are changing. So if I just take xt as 10 from my earlier list, if I take this as 10, my t plus 2, like I will skip one value, I will just another value as 14. So that's why you see first value, this is xt and this is xt plus 2. So you take xt plus 2. When again you will take 12, can you tell, if I take xt as this 12, can you tell me what would be my xt plus 2? D'Costa?
Yeah. So xt plus 2 is going to be 6. Sorry.
Perfect. Yeah, I think you are on right track. So yeah, if my x2, if this is my xt now in next turn, x2 equal to 12. So if this is t plus 2 would be 4. So x4 is you're 16, right? What I think you were on the right track, but somehow you can get confused. So it is 12 and 16. Now tell me, Arka, can you try, like, for x3 equal to 14, what would be my xt plus 2? If I talk about x3 equal to
Uh,
14, yeah,
can I have the series in front of me?
is
I think
there?
it's up.
Yeah,
No,
this
like
one
at a
here.
stretch. Oh, okay. So yeah. Okay. So x3, it should be 18, right? Plus 2.
Yes, yeah,
X5.
x5
Yeah.
is 18. So what we will use at the last term would be 14 and 18. So what you see 14 and 18 here, and these are your again averages. Docosta, Orca, all both clear. Like calculation, the rest of the calculation part remains same.
Yeah.
Yeah. I'm good.
Cool. So this is with leg 2, and similarly, you can talk about leg 3. You can just go through if you are interested, and like how you calculate variance thing is normal. Why I'm calculating variance in step 5? Because I need to calculate autocorrelation. So how do I calculate autocorrelation? I will calculate autocovariance divided by variance to get a autocorrelation. So I'm calculating variance so that I can derive autocorrelation, because in general, as I told you previously, covariance is not of much use. It's a correlation which helps you making decisions. So same applies with time series also, with normal data set as well as with your normal time series. So I calculated the variance with our normal formula that we usually talk about using this, and my variance is 8. So now I have got things 14 as my mean, variance as 8, and I have auto covariance for leg 1, leg 2, leg 3. So calculating auto correlation for leg 1, covariance was 4 from the first calculation, and my variance is 6. So I can calculate auto correlation with leg 1 as 0.5. Similarly, auto correlation function for leg 2 is this. Like, and you can talk about autocorrelation for leg 3 is -1. Are we clear? This is a summary of autocovariance, for leg 1, leg 2, leg 3, and autocorrelation leg 1, 2, 3. See, to be honest, these calculations this can be done in Python for big data set also, but it is important that how values are coming, so that tomorrow, once you are in a decision maker's position, you have every single detail to make your decisions. So any doubts in this? So otherwise we can jump on this. So and we can jump on this slide. It was just to get you an intuition how the autocovariance or autocorrelation is calculated. All good?
Yeah.
Okay, thank you. Is the understanding better on these terms now?
Yes.
Autocovariance, autocorrelation. And if you plot autocorrelation function, so when I say autocorrelation function, ACF, you saw that we were talking about autocorrelation function with variable 1, like tau 1, tau 2. Like in general, I can talk about ACF for tau. And if I plot this, see autocorrelation of say 0, like I can talk about autocorrelation function with leg 0 also. Like we calculated leg 1, leg 2, like we went till leg 3, but one can talk about autocorrelation function at leg 0. That means correlation of variable with itself. So what would be that? That would be 1, because you're just talking about the lag. These are lags. On the horizontal axis you see lags, on the vertical axis what you see the correlation. So if I talk about leg 0, your autocorrelation is 1. Likewise, you can go like for one if one leg is tau equal to 1, you have some say around 80% approximately, and likewise you can go on till this one. If you skip say 50 days of data, if say for example if you are calculating returns, and when you are calculating returns, you are comparing say day for yesterday Friday's price, like Friday's price versus initial 50 days back price. So this is a t equal to let me write today minus 50, something like that. So this the correlation of current one, that is Friday's one, will be very less with 50-day lagged variable. Like, so this autocorrelation function, this is an autocorrelation function wherein you plot lags versus correlation. Are we good? Shall we move ahead? Please trust me, I could have just read these three lines and went ahead, but it's my like the, you can say, passion to ensure patience to ensure that the knowledge is transferred. So are we good on this one?
Yes.
Okay.
On my side.
Yeah, Arka, got good?
Yeah, all good.
Okay, so let's talk about something which is very special and it's important from exam point of view also, white noise. So white noise refers to serially uncorrelated time series. So a time series that is serially uncorrelated. So even with ACF1, you will get some number correlation which would be too low. So that white noise refers to serially uncorrelated time series that has mean of 0 and the constant variance. See, of course, if you notice these two properties, the mean should be stable and variance should be finite and stable. Of course, this is a covariant stationary time series, but what happens that if you're if you have a very uncorrelated time series which has a mean 0 and constant variance, that time series is called as a white noise. A time series is serially uncorrelated if it exhibits no correlation amongst any of lagged variable. Say for example, if you are not trying to establish any relation, say if I have 30 days of data, say D1, like, or say price 1, price 2, price 3 for and price 30. Now whatever we did, like we calculated covariance of this, taking these two. If you calculate ACF using this, the correlation is quite low. So if it exhibits no correlation amongst any of its lagged value, then you say that your time series is white noise. Okay. If the observation in white noise processes are independent as well as uncorrelated, the process is referred to as independent white noise. Okay, so just addition of independent. If the observation in the white noise process are independent as well as uncorrelated, the process is referred as a independent white noise. See, of course, stock price is something which intuitively are not dependent, but yeah, you can talk about returns. And but yeah, in general, you can talk about white noise also. You can talk about independent white noise also. Okay, so you need to, but yeah, largely like we talk about white noise, but yeah, very important to know independent white noise as well. If the process also follows a normal distribution, it is known as a normal or Gaussian white noise. If you plot this data, uncorrelated one, and if that distribution is normal, then you say it is Gaussian or normal white noise. You can just let's refer to, like, let's stick to the term normal white noise. Gaussian, you may forget or get confused, but yeah, these are one and same thing, normal or Gaussian white noise. It may appear two things, but it's one and same thing. So white noise, if I were to tell you in a very simple thing, if your time series has a 0 mean, constant variance, and it exhibits no correlation amongst its lagged value, then you say your the process is called as a white noise. Okay, yes, no, all good?
Yeah, I'm good.
Dacosta, any doubt?
No, I'm okay.
Thank you. Let's move ahead. Now, the above topics were little like, at least now your understanding at least would be better with this kind of explanation. But yeah, now relatively lighter topics. The above ones are like, people find it a bit difficult from my experience of when I translate this. But yeah, next one is AR1. It is autoregressive. So can you tell me, we talked about regression, linear regression. What do you understand by regression in general? Like at that time also I covered. What we understand by term regression?
Regress the dependent variable with the independent variable. It's like regressing something with
Yeah,
something else. Yeah.
yeah. And Acosta, agree? Anything else you want to add?
Oh, I'm good.
Yeah. So when we talk about regression, it just I'm trying to estimate my dependent variable from some some variable on which my y depends. My y is dependent variable, my x is independent variable. I'm trying to derive some pattern. Like yesterday we were talking about line plots, right? We were talking about line plots, and we were trying to establish this line so that if someone asks me if your x value would be this, what would be my corresponding y value? See, reality I can't predict where this value would be, but I have established some line which can get me this y value. I can use this as an estimation. Like I can make some decisions that my y value would be near to this. Okay, so this was linear regression. Now I'm talking about auto regression. Largely things remain same. It just you're trying to regress. Now instead of y and x being two different things, you're trying to regress y from its past value. So these values that you see on the horizontal axis would be your just the intuition. Of course, I will talk about what is autoregressive, but intuitively you're trying to establish your dependent variable from its lagged value. Is it clear? Are you clear with the term autoregression? Like autoregression means you try to estimate your, say I'm trying to estimate what would be end of day Apple stock price or Apple stock returns based on how it has done in this last week. That's the auto regression. Are we clear? Like on this one?
Repeat what you just said.
Yeah. So let me linear regression, you are trying to say your stock return was function of, this is your independent variable, and your it was function of, say b0 would be y intercept. You will have some b1, say, which would be your S&P level, S&P 500 index level, plus rate of interest b2. It would be b2. This is your b1, this is your x1. So this is your y variable, and you have got corresponding x variable. This is your x1, x2, and third variable, say perhaps could be, we can talk about GDP, say x3. Okay, so in this, what we talked in linear regression, we had two variables. One was stock return. These variables will differ. I was trying to establish or estimate what could be my stock return if my stock returns were dependent on S&P 500 value, rate of interest, and GDP. Is it clear what we mean by linear regression? Over there, the variables were different. Y and X were different. Are we clear so far? So that I can explain you to the auto regression.
Yes.
So in linear regression, different. Auto regression, you're trying to estimate stock return from past stock return. Say B0 would be there. Say B1 plus some, say past 10 years stock returns, just as an example. So over here, the difference is, like over here, your dependent variable and independent variables were different. Over here, your independent variable is y, and your dependent variable is y, current stock returns, and you're trying to establish current stock return from stock returns some time in past. That is the only difference between linear regression and auto regression. Make sense, Acosta?
Kind of.
What's the confusion? Like, let me know. Like, see, but intuitively, do you agree? Like, was, whatever happened with stock price of Apple last week, that will more or less impact this week price also. Intuitively, you agree, or like any other views?
Like when what
Mm-hmm.
happened to Apple stock last week
Hmm.
will impact what happens to it this week.
Yes, like yeah, that's the idea of auto regression. Intuitively, and there could be some, see, these are different views, like when research happens, right? So few researchers, like, see, this is a, actually you come up with model. One model is, say, Orca come up with this model that my stock returns are actually can be established, estimated using this, and you come up with this return. No, I feel that past past stock price is deriving the current stock price. So what we can do, we can apply both models to estimate, say, tomorrow's value, and we can see that whose value was more accurate. Like, see, case scenario could be different for this, or there's some, at some cases this model may work well, some cases this model may work well. So in real, but yeah, uh, it's it's quite evident that at some point this also works, largely not with a stock price, but say your GDP. Whatever was your GDP, like high level, that you can derive current year GDP using the past year GDP, because those are quite static variables. Those do not move that dynamically. Stock price is something which is quite dynamic. So you need something better to capture your stock price or stock returns, whereas something which is quite static in nature, you can use these things.
Yeah,
Agree, intuitively making sense, Costa, or like you need more explanation?
I'm good.
Good.
Yes, I'm good.
Okay, so like whatever I said this here, like I'm just translating in the mathematical equation formula. I can regress my current day w- dependent variable value using my past day, like one day before value. So yt can be estimated using yt minus 1. This term d is quite similar to intercept term b0 that we were calling. In autoregressive, we call it at d. Like, it's a notation as such, it doesn't change much. Intuitively it remains same. And of course, error term, like whatever would be when you estimate, when actually this is the estimated value, say you will observe this value. So like from past one, you can add some average error term, like you can see, you can derive something average of these error terms, right? So you can add it, like just to have a better approximation. But yeah, largely AR1 is something which you try to regress from its past value. And D is intercept term, YT is current value, the YT, the time series value being estimated, what you're trying to being estimated. And this is one period lagged observation. Like, this is something which is T minus one period lagged observation. Current random variable, white noise shock, mean zero. Like the, like you can say just a error term. Don't make yourself confused. Phi is coefficient of lagged observation. Like, phi is something which is quite similar to b1. It's kind of a slope. Change in yt minus, what is, if your yt minus change by per unit, what is a change on yt? This is a coefficient term. Like how we say for example, uh, your, I think we saw one linear regression, or let me just share you. But yeah, this is a coefficient or a slope term, what we had in a linear regression. Okay. Are we good on autoregressive? Are you making notes simultaneously, both of you?
Yeah, whenever I try to just write something, I lose concentration. So I just want
Ah,
to,
okay. No worries.
because
So what you can do, I
you give,
completely agree with your point. So what you can do, in class, you just listen to me, and you can
and then
later on
watch
you
the
can
video.
and just
But
make notes. That would be, I think, yeah, but I agree. I completely agree with you. So yeah, fair point. Cool. Let's move it. But we are clear on autoregressive, right?
yes,
Okay, and very important note, just make a note of it. We can, I'll just touch upon this when we will talk about one topic which is called as unit root. Okay, AR1 process is covariance stationary if phi is less than 1. So if your phi, the coefficient of lagged variable, is less than 1, you interpret that your time series is covariance stationary. Sometimes you might be given that this is our AR1 equation, like very big question, but the somewhere the basic idea would be this, like you just have to notice a p part and comment that if it is a covariance stationary or not covariance stationary. Okay, so very important point. Later on, whenever you would be watching, make a note of this point. Can you tell me if it is not covariance stationary, if phi is greater than 1, my time series is would be non-stationary and it will be upward trending, like how I was showing you, like a stock price. That would be, we will talk about next chapter, which is non-stationary time series. And moving average is something like, see, first of all, like if I were to draw some time series of stock returns, it could be something like this. Say this is a February 2020. Suddenly March 2020 comes in. Like you had some return like going up later in, but yeah, this is something which is called as a shock. So if you are estimating current value using, now there are two things. We don't have an intercept term. We have a mean and your one lagged error term. This is the error term as in, or a shock. You can say one period lagged random white noise shock. These are shocks, right? This is like kind of a slight outlier. So you use that outlier along with the mean to estimate current value. That process is called as a moving average. Is it clear? Any doubts? Yes, no, like, yeah, what if doubt, please like be specific.
No doubts from
I'm
me.
good.
Oh wow, fantastic. Like and very important point, make a note of it. Testing area, from exam point of view, these 4 points. So yeah,
moving average and autoregression has the same like function, just that's different variables.
Objective is
autoregression has
yeah, please go on. In fact, I'll get a surety that you understood and you're able to reproduce. Please go on. Yeah,
autoregression has yt equals to d plus the sign.
phi. Yeah, phi. It's a Greek letter phi.
Yeah, phi, and then error t minus 1 like this. Plus
perfect. Yeah.
Error.
Yeah. High level idea is you are just using lagged variable and intercept term to estimate current value. Here, can you comment about moving average? Dacosta, any statement, similar statement, if you could make for moving average as well?
Yeah, so moving average is also like having this mu plus sigma, then error t minus 1 plus the error.
Yeah, this is kind of, yeah, this is like just, of course I understand, like we don't use quite frequently. This is Greek letter theta. So your mean, yeah, that's perfectly fine. See, as long as you convey idea, I really don't like, to be honest, when you are interviewing or getting interviewed, use notations carefully. But yeah, to be honest, for me, if you convey idea, I know you in exam you will get right answer if you have a fair understanding. Over there, these doesn't matter. But yeah, this is theta, this is mu, which is mean. So mean of time series plus some coefficient of error term, one lagged variable, lagged error term. So epsilon t minus 1 theta plus epsilon t. So that is the moving average. Now, very important thing, moving average has very short-term memory. Abrupt correlation cutoff of the first displacement Very important. Can anyone try telling me what this it could be? From the calculation that I was showing you in five, when we took five numbers, we tried calculating uh, for say even for t equal to 1, tau equal to 1. If you try calculating, say you had x1, we had some number, right? X1 equal to say 50, x2 equal to 30, and x3 equal to say 70. When you were calculating, say what essentially this is technical, so let me explain. So when you are calculating yt, you are just having an impact of error term in this value, right? Like this, when 50 is estimated, you are having an impact of that error term in this 50. But for your covariance, when you are calculating correlation or covariance, first you will take these two pairs, right? But when you take a second pair, it will have an impact of this, right? This would be this would be considered. So anyways, where we had a shock impact, that element is just considered one. Rest of the variables are quite stable, like x2 x3 won't be having a shock impact. So it says moving average 1 has very short term memory, abrupt correlation, autocorrelation cutoff. So like when you calculate for tau equal to 1, your correlation, when the impact of this error term is there in first term, your correlation might be very high or low, but yeah, it would drop significantly, or it would change significantly after first displacement. After you have taken these value x1 and x2, when you take x2 and x3, the whatever numbers you will calculate would be quite different than what we had with the first value, which had a shock impact. Is it making sense intuitively? Like, of course, I'm not going to a calculation part, but intuitively, once you have factored impact of error, now this would be a new benchmark to, like, in a way you can say, like once you have derived yt, which is an impact of shock, now next yt plus 1 can be derived using this value indirectly will have a shock impact. But now say yt minus 1 and yt, when you take a shock impact in this circled value, it would be quite different than yt minus 1. But now this is new benchmark when it would be used to calculate yt plus 1 using autoregressive. But yeah, when you use moving average to arrive yt, you will have some spike from this because you're taking a shock impact. But when you move from here to here, like the impact will go off, so there would be a quite the autocorrelation will be kind of this term is used, cut off after first displacement. First, once you move from here to here, the autocorrelation will drop significantly. Is that clear? Will you remember this? Intuition is this. And but yeah, you need to remember for moving average 1, after first displacement, autocorrelation cutoff is there after first displacement. Any if you understood, great. Otherwise, just for your benefit, remember in moving average, autocorrelation cutoff in MA1, autocorrelation cutoff after first displacement. Had this been MA2, autocorrelation cutoff after the second displacement. Okay. Yes, no, at least give me some, like at least if you understood, great. If not, at least you need to remember this line, very, very important line.
I'm sure we'll get a full clear picture like as we move on.
Yeah, certainly. Yeah. And one key feature of moving average process is called as a autocorrelation cutoff, like that we were just talked about. We would compute autocorrelation using the formula. See, you can calculate for one method is like the method I told you for autocorrelation. Another way to calculate autocorrelation is use this coefficient theta, like theta 1 divided by 1 plus theta 1 square. This will give you the autocorrelation. The another way, I mean, no need, like if you remember, great. If not, because in exam, this calculation that I shown you on PDF may not be tested, but this can be asked because the formula is quite straightforward. You can easily calculate just coefficient divided by 1 plus coefficient square. So this is can be asked. This of course what I shown you in the PDF, it was just for your understanding, so that you have insight what's happening. But yeah, just make a note of it whenever you'd be making notes. Leg operator, it's like I'm trying to arrive at this number in general. So what you see here 2, I'm trying to arrive this at 2 using like you do simulate, like you check what is like power of this L when I'm trying to compare yt minus 2 and yt. What is coming as a power of 2, that is called as a leg operator. The notation of leg operator is L to the power m yt equal to yt minus m, where yt is value of time series at time t, current value, and the m is the number of period before time t. For example, this term L to the power m is called as a leg operator. I mean, nothing much information given here, but yeah, you can just remember. If I were to regress, say, mth lagged value, if I were to compare, say, 1 month old data, t minus 30, with the current data, yt, say yesterday's, what is some constant to the power m? This is called as a leg operator. Okay. Just I mean, nothing much here. I mean, I haven't seen any questions around this, but yeah, given it's part of your chapter, you need to know. Now compare, if I combine your AR1 and moving average 1, you can come up with autoregressive moving average, what is called as ARMA, wherein you use both. One is your intercept term, coefficient term, phi, Greek letter phi, with multiplied with one lagged variable. Like this error term is constant, and you take shock term also. You take theta, coefficient of lagged random shock, and theta minus 1. Can you tell me which term is missing from moving average? First tell me what was AR
The
equation.
mu.
Perfect.
Mu is missing.
MA.
Yeah. In can you tell me what was Patagosta? What was AR equation and what is moving average equation? Or Arka, you tell AR, simple one, and let me ask difficult one to Augusta.
Yeah, so AR is essentially, yt equals to some intercept plus phi of yt minus 1 or t minus k plus, an error term.
Yeah.
That's autoregression.
Yeah. Augusta?
Yeah, so that was mu.
Perfect.
Yt is equal to mu.
Yeah.
Plus sigma
It's
error term.
Theta into your error term.
Theta error
into
term t
plus-
minus.
Yeah. So when you compare, when you build ARMA model, this mu is dropped because you have one lagged variable. If you notice, intercept term, coefficient term, and error term. So yt minus 1 lag value is there, error term is there, their coefficients are there, but mu is not in ARMA. Just remember this. Okay. Rest notations remain same what we talked in during AR1 and MA1. Okay. If autocorrelation gradually declines, the analyst should consider AR or ARMA. Very important point. Sometimes you might be tested on this general area. If your autocorrelation is declining gradually, when I say gradually, so when we talked about one term during moving average, we talked about autocorrelation cutoff. I will show these things to you pictorially just to get you better understanding. So autocorrelation cutoff, and so this is something some when something which had a correlation here, once you applied moving average, correlation would be here. There would be a significant drop. By cutoff, I mean this phenomena. And when you have a gradual decline, you will have a first value here, leg 2 value like this, leg 3 value like this. It will decline gradually. So when there is a gradual decline, you will use AR or ARMA model. Is that clear? Like, will you remember gradual decline, autoregressive, or ARMA? If you have a autocorrelation cutoff, autocorrelation cutoff is a feature of moving average time series.
Okay.
Is it clear, Orca? Making sense, or like?
Yeah.
Any,
So the and
Yeah,
in
I'm
which
good.
case do we use the MA?
yeah, Doctor sir, can you say again? Sorry, maybe I
Yeah.
got.
So I'm just asking. So just to be clear, so
Mm-hmm.
that I just get understanding now.
Mm.
So in which case do we use the MA? Is it when
MA
it's
is, yeah. So if you have decline, like if you notice that if your autocorrelation has declined when you use say tau equal to 1 and tau equal to 2, if there is a significant drop in autocorrelation, then you will use moving average. If your autocorrelation is gradually declining for
okay.
making sense.
Uh,
Yeah.
yeah, it's making sense.
Okay. Now, testing autocorrelation, again some bit on hypothesis testing, but you don't have to you don't have to solve questions on this, like how we solved questions for b1 equal to 0 and b1 not equal to 0, for all ba1 equal to 0 and at least one ba1 not equal to 0. This was multiple regression where we did the f test, and this was your linear regression one variable. There we did t-test. Over here we will talk about some very like Orca might be using, not sure, I mean he might be quite close to this, but yeah, these are a bit advanced tests which are used for uh, doing hypothesis testing for autocorrelation. And these are something which are in your syllabus. You might be asked some questions on this. On this one, you are just expected to know few things that I will just tell you. We see that time series is white noise by testing null hypothesis. So now you want to test hypothesis. If like your hypothesis is given that there is a shock, like something which is a null hypothesis is that your time series has a shock, and null hypothesis is that autocorrelation are equal to 0. There is no, like if you remember when we were understanding white noise as a term, we ensured that we read that your terms do not exhibit, your terms are uncorrelated. So my null hypothesis is that I want to prove, see, eventually I want to prove there is no shock in my time series. So null hypothesis, I'm assuming the time series is white noise or terms are not autocorrelated. That is your null hypothesis. Is it clear first of all? Like any confusion with this? Is the null hypothesis clear to you? Like just formulating hypothesis. Forget about these three terms for a moment. Like, see, first of all, uh, if you are a like researcher, you have some time series, like somewhere you see small shocks, right? Not something like very big shock. So what you want to prove that your time series do not have white noise. That means your terms are correlated. I can estimate tomorrow's term using current value. So as a researcher, your belief is that your time series has a autocorrelation. I can derive my current value using past value. That is a researcher's belief. So if I want to perform hypothesis testing, negation of researcher belief is no. I would assume that there is a shock. But with one shock, I cannot say that my time series is white noise. I have to prove using hypothesis testing. I have to apply some statistical tool to say this thing that I was claiming that my time series do not have white noise, I have to say that with 95% confidence. I cannot just make statement based on my observation. Of course, making observation is kind of a seeding to the hypothesis testing, but you need to prove something with some confidence, statistical tool. So null hypothesis there is your time series is white noise. Is the understanding clear? Like how do you test autocorrelation? Lacosta, like I need some input. Like not clear, then tell me what. Like try saying
not
something.
not too clear. Not too clear. It's
Yeah,
not
like
too clear so far.
no worries. But what's not clear? Like say something so that I can try understanding from that where are like gaps. I can try filling those gaps, perhaps. Like that. Yeah.
Okay, so based on the statement here,
Yeah.
I'm just
Please.
thinking that maybe the hypothesis is always going to be zero, because from the white noise, the functions or the characteristics of it, so the mean has to be zero. So does that mean now equals white noise? That's like the null hypothesis is going to be equal to zero.
It's not really null hypothesis equal to zero. It's just like yeah, I got your confusion. So when you say null hypothesis over here, like we do not have something like mu equal to zero or something like that, something we can explore. But as a statement, if I were to say as a statement, I will say H naught is my time series has white noise. Okay, how we do translate it in mathematical terms, calculation part is not there. You just need to remember what is null hypothesis when you test autocorrelation. When you test autocorrelation, you just say my time series has white noise. Or what you say, if I were to tell you mathematically, you say all your autocorrelation, say all, let me call this as ACF, autocorrelation functions are zero. Whereas I would, as a researcher, I believe that autocorrelation function, this is something I can check what are the notation used, but intuitively I believe that it should be the case. Your autocorrelation function not equal to zero. I'm saying as a belief or a researcher that my time series is autocorrelated, or I can estimate current value using lagged value. So ACFI not equal to zero. That means there is a autocorrelation. Autocorrelation is not zero. That is my belief. But as a negation, as a hypothesis process, I will assume that autocorrelation function is zero, not really mean. So over here, like we are focusing mainly on autocorrelation, not really on a mean when we talk about the testing hypothesis for autocorrelation. Is it making sense? Some more or less, or
Yes.
still not clear?
It's making sense now.
Okay. So the next point is like how we had test T and Z test. Over here we talk about box Pierce Q test and Eljung Bock Q test. You just have to remember these names. You don't have to use any tables, or from the FRM point of view, you don't have to use like these tests calculate. Like third step was critical calculate. That part is not there. You just need to remember this hypothesis testing, and like you might be given, yeah, this is a box Pierce static, this is calculated. Then inference part you might be asked, but that taking value from table or calculating the static or box Pierce or Q static is not in the scope. But yeah, very important point, you use Eljung Bock test when your samples are small. This is something which you should remember. Sometimes you may get low hanging fruit in the exam and you might be like asked to this question. Okay, so yeah, small samples Eljung and big sample Bock PS. Rest you can ignore. This is something which we already discussed. So autocorrelation, testing autocorrelation. Shall we move ahead with these pointers?
Yeah, sure.
We come to end of this chapter. So help me solving these questions. covariance stationary variables have all except which of the following characteristic. So covariance stationary should have all the characteristic listed below except which one? Please try any one of you please answer.
I think it's option D.
It says covariance stationary variable will
have all.
except
Okay.
yeah.
Yeah.
This is in fact primary condition. D is primary condition.
Mean should be finite, right? So
again, looking at the option, I believe now except shouldn't be there. Like, yeah.
Sometimes, what happens, it's very confusing because on the test, it's the language can, yeah.
We just talked about.
Is it C?
Variance should be.
No, I think it's.
Mean has to be constant, right? Mean has to be constant for covariance stationary.
Yeah, finite and stable mean.
Finite and stable mean, right?
For both mean and variance, these should be finite and stable. We don't really talk about covariance there, but finite covariance and variance, but infinite mean.
So option A is out. Option D, yeah, finite covariance.
Let's see, because to be honest, even I think that except shouldn't be there and D should be the answer. That's my hands, but yeah, let's see what they have. Yeah, I think except shouldn't be there. Like I would imagine, like this.
I think the language of the question is
not
very confusing.
Yeah, not good. Agree. Yeah, but yeah, I mean just a basic question, so ignore that. This one. An ARP model differ from MAQ model in which of the following? I think this both of you can answer. So just go through this. You can just, instead of P, you can just think 1-1. Like if you don't have exposure, it's just P and Q. If you include 10 legged shock, it would be MA10. If you include 10 legged variable, it would be AR10. That's the only difference between P and Q. But yeah, you can take example as 1-1 and think that what should be the answer.
Yeah, I think it's option B, AB. Because C and D, it doesn't show any exponents. Yeah, option B is.
DaCosta, your views on option B? Like, can you just comment anything, like what you feel about option B?
Just a moment.
Sure. Take your time. Like it's the same gradual decline in correlation and autocorrelation cutoff. It's like related to that.
I think it's B.
Yeah, agree. Even I feel so, because it says MAQ moving average will have a autocorrelation cutoff and AR will have a decreasing autocorrelation structure. That I think we discussed over here. Like if you remember, like this was something gradual decline and the autocorrelation cutoff. So this is a answer. So I would think B. Yeah. And this is the explanation, but yeah, we covered this in this thing, but yeah, you can always go through this. Now, this is something which I think this would be too much at the moment, but this is slightly exam level question. Do you want me to cover it now, or you will watch recording once, then we can take it up, like either ways?
So I think, PSCF is given, right? So lag 0 and lag 1 are out. It's changing at lag 2. So it's either option.
Okay, I think we lost you. Are you saying something?
So I think it's option B, AR2.
Okay, I think we lost you. Can you just repeat? I think you just looked at it and commented, and your net was disconnected. So can you repeat what you said?
Oh, okay. Yeah. Because if you see the autocorrelation structure, it's decreasing, right? That's it's slow decreasing. And if you see the PSCF, it's the structure of PSCF is getting changed at lag 2. So
perfect.
So it's
fantastic.
So it's either B or D, right? So it's either B or D.
Yeah. I think you're like you spotted right. So Docosta, for your information, we are given certain autocorrelation structure and partial autocorrelation. So from autocorrelation, you can like as Orca mentioned that there is a gradual decline in autocorrelation. It's not really immediately dropping. Like if you see be very careful this just I'm just give explain telling you this from explanation purpose. Like over here you see there is a gradual decline, right? But it is in partial autocorrelation. Had this kind of structure been in autocorrelation, we would have said that it is a moving average, but your autocorrelation is moving gradually, right? It's not really something happened from here to here. Had this been a case, we would have said that this is a moving average. But given this is gradually declining, we conclude that it is AR model. Agreed, Augusta? First of all, like first we are concluding which is it AR or moving average. So we concluded because there is a gradual decline, it is a AR model. Agree, Augusta?
Yes.
And second thing, what Arca spotted, now we spotted, now option C and D are gone because they say moving average. Option A and B says auto-regressive, but it is it one or two? But so what Arca mentioned is partial autocorrelation. It is up disappearing after like this is disappearing after the second step, so it should be AR2. So this is how had this been this is would have been small, we would have concluded this to be AR1 because this partial autocorrelation is declining after that. It says AR2. Okay, so that's the thumb rule. To conclude about autocorrelate AR or MA, you can look at this autocorrelation cutoff, and is it one or two? You refer to partial autocorrelation. Okay.
Okay.
Yeah,
Yeah,
that's
sure.
the like a hint, or you can say like how you should interpret. So it's AR2. Like he
Mm,
is spotted at at the glance. So great. And this is something which is like as I was saying that if you want to learn this advanced in Python, these are just plotted from some data. But yeah, I mean, no, I mean, just be familiar with this question. Somewhere, what should be asked is these kind of things that we covered in today's class. Okay, so yeah, this is all about this chapter, and I think we were done. But yeah. So let me just stop recording and discuss.